quickly, let's look at 5.1 and look at a couple examples. This will help us make more sense of some of the things following in Chapter 5, because there is a relationship between two types of functions that we do, and the relationship between those functions is if they are inverses. So inverses have the x and the y values interchanged. So if you watch the videos in my math lab, they should have gone into that. I'm not going to focus so much on whether or not you understand what it means for a function to be a one-to-one function, but I do want you to know how to get an inverse. If we have just a single ordered pair, the inverse of that comes from swapping the x and y coordinates. But if we have an actual function, such as f of x equals 4 over x plus 9, if we want to get the inverse of that function, then we essentially have a four-step process. We begin by changing f of x to y notation and writing the rest of the function. And then, everywhere we have a y, so that was step 1. Step 2, everywhere we have a y, we're going to change it to an x. And everywhere we have an x, we're going to change it to a y. So now this actually is the inverse of the original function. But we want to solve this for y so that we can put it in function notation. So in order to get rid of the fraction, let's multiply both sides by y plus 9. Y plus 9. So on the right side, the y plus 9's on bottom and top cancel. On the left side, we have y plus 9, not 4 plus 9, but y plus 9 times x. Now we could go ahead and distribute here, or we could divide by x and then move the 9 over. So it doesn't really matter here. In this case, we'll divide both sides by x. So we get that y plus 9 is 4 over x. And then, of course, to get y by itself, subtract 9 from both sides. So y is 4 over x minus 9. So that is step 3. Once we change the y to x and the x to y in step 2, step 3 is to solve what we're left with for y. So this thing we end up with, this is our inverse as a function. So since we call the original function f, the notation we're going to use for this one is f with a superscript of -1. That doesn't mean we're raising our function to the -1 power. That's just what we use to describe this as the inverse of that function. So our inverse is 4 over x minus 9. Let's look at an example and see that when we plug a particular value in to this function and get an answer, the inverse of that is a solution to the other function. So if we take f inverse, and let's suppose we plug in a -4. If we substitute a -4 into this function, we have 4 over -4 minus 9, which is -1 minus 9, or -10. So for the inverse function, a solution is -4, -10. Which means that for the other function, the regular function, 10, -4 should be a solution, if we did that correctly. So we take our original function, which is 4 over x plus 9, and we're missing a sign, aren't we? -1 minus 9 is -10. So if we substitute a -10 into this function, we should get an answer of -4. So 4 over -10 plus 9. Well, -10 plus 9 is -1, and sure enough, we get -4. So this ordered pair is a solution to the inverse function, this ordered pair, which is the inverse of that ordered pair, is a solution to the function f. And that's going to be true for every ordered pair. Anything that is a solution to f of x, the inverse of that ordered pair will be a solution to the other function. Hence, this function gives us the inverse of this function. Every ordered pair is the x and y have been interchanged. Now, let's look at another result of this, is that when we do the composition of a function and its inverse, something special happens. And let's look at this by example. So on the last example, when we put in a -4 into the inverse function, we got -10. So that was for the inverse function. And when we put 10 in, we got -4 for the regular function. So let's evaluate this for the x value -4. So remember how composition works. We do the inside first. So substitute -4 into f inverse. And when we put -4 into f inverse, that's -10. So the inverse function changed this x to that y. Well, the function f takes -10 and changes -10 into -4. So it undid what f inverse just got through doing. So our answer is just our initial input. We can do it in the other order as well. If we put the function on the inside and the inverse on the outside, f of -10 is -4, so this function changed a -10 into that number. And f inverse takes -4 and changes it back into a -10. So it undid what the function did. So anytime we take the composition of a function and the inverse of that function, they undo each other, giving us that original input. And that's one of the main reasons we wanted to look at this section, is because when we get into the following sections that deal with two functions that are inverses of each other, we do need to know how inverse functions interact. But for homework, you're going to be given a function and asked to find the inverse function using those 4 steps. So that's 5.1. 5.2, we're going to look at a specific type of function, and we'll look at this as an example. This is called an exponential function. So the thing that makes it an exponential function is that our variable is the exponent. So we want to begin by graphing this function. If we substitute a 0 in for x, 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, and let's also put some negatives in. So 2 to the -1 means 1 over 2 to the first, which is 1/2. 2 to the -2 power means 1 over 2 to the second, so 1/4. Now if we graph those, we have 0, 1, 1, 2, 2, 4, -1, 1/2, -2, 1/4. So as we go to the right, we get steeper. As we go to the left, it turns out that we are never going to cross the x-axis, because if we substitute negative numbers in, we're not going to get a negative answer. We're just going to have 1 over 2 to that negative number change to a positive. Well, 2 to any power is a positive. 1 divided by a positive is positive. This is just getting closer and closer to 0. So y equals 0 is a horizontal asymptote for this graph. We're getting closer and closer to the x-axis. And then we discussed what happens if we add a constant to our function. If we add, let's say we add 3, it shifts the whole graph up 3. So not only will each point go up 3, but so will our horizontal asymptote. If we subtract a number from our function, then everything, including the horizontal asymptote, will go down. So let's look at another example of this. Let's suppose our function is 3 to the negative x minus 2. So since we have a number added or subtracted, that's going to be our horizontal asymptote. It's going to be down 2. And then to figure out exactly which direction our graph is going, negative 2 and positive 2. That doesn't mean that's the domain. That is just enough positive and negative numbers to give us a pretty good picture of what our graph should look like. So if we put in a negative 2, we have a negative from the formula, and then 2 minus a negative is a positive, so we get 3 squared is 9, minus 2 is 7. If we put in a negative 1, we have a minus and a 1, so 3 to the first is 3, minus 2. 3 to the 0 is 1, minus 2. 3 to the first, negative, if we put a 1 in, 3 to the negative 1, that's 1/3 minus 2, which if we do 1/3 minus 2 in our calculator, we get about negative 1.7. If we put a 2 in, we have 3 to the negative 2, so that's 1/3 squared, or 1/9 minus 2. So that gives us about negative 1.9. So we can graph those, and remember we have a horizontal asymptote at y equals negative 1. So we pull up our graph, we come into negative 2, and there's our horizontal asymptote. And now let's just look at the table. Negative 2, 7. Negative 2, 7. Oops, I changed our pen. Negative 1, 1. 0, negative 1. 1, negative 1.7. 2, negative 1.9. So in this case, our graph is going down from left to right instead of up from left to right. But it still has that same generic shape, that exponential shape. It's going up from left to right, and it was getting steeper and steeper and steeper. This one was starting out steep, but it's going down from left to right, and it's getting flatter and flatter and flatter. I'm not going to ask you to memorize when does it go up, when does it go down. It could even be that we have some that go like that or go like that. But I'm not going to ask you to memorize that. You just make a table, draw your your horizontal asymptote, plot your points from your table, and then you'll be good. So the other thing we want to do in this section is look at an application of an exponential function, and that's compounded interest. The formula we use for compounded interest is A equals P times 1 plus R over N to the NT, where P is our principal, which is our starting amount. R is our rate. It's going to give it to us as a percent, but we want to put it as a decimal into our formula. N is the number of times we collect interest per year, or pay interest depending on which end we're on. And T is the time, which that's going to be years. And A is just the value after time T. So if you were going to take out a car loan, if you were doing an investment, this is how you would find out the value of your car loan after a certain amount of time. How much are you actually going to have to pay back? So let's look at an example. Let's suppose we want to borrow $5,000 and we're going to have to make a payment every month. So we're compounded monthly. So if we're compounded monthly, there are 12 months in a year, so compounded 12 times a year, so n equals 12. We're going to be paying at an interest rate of 5%, and we're going to take 5 years to pay this back. And we want to find out how much are we actually going to be paying back. We're not going to be paying just the $5,000 because the bank has to make money when they loan out money. So that's how they make their money, is they charge interest. So in place of P, we're going to put 5,000. In place of R, we're going to change 5% to a decimal. So I remember D comes before P. If we're going from percent to decimal, we move to the left, and we always go 2 places. So that would become 0.05 as a decimal. So 0.05 over n to the n times t. So what this piece here does is it breaks down our rate, and we're not charged 5% this month and 5% next month, and every month charge 5%. 5% is your annual percentage rate, APR. So this fraction takes the annual percentage rate and cuts it down to an interest per compounded cycle. So 5% divided by 12 months, about 0.417%, which then that would be changed to a decimal. So that's what this is. It's not charging us the full 5% each month. It's just charging us a portion of that 5% per month. The exponent, I guess I should erase that. The exponent tells us how many payments we're making. If we're paying 12 months a year, then 12 payments per year for 5 years. 12 times 5 is 60, so we would be making 60 payments. So let's find out how much this loan is going to be valued at after 5 years. So 0.05 divided by 12 plus 1, that's what goes in parentheses, 1.00417. And then we're going to raise that to the 60th power. And I'm not even going to take that out of my calculator and type my rounded off. I'm just going to leave all that in. Raise that to the 60th power. That's what this part makes. Then we're going to multiply that answer times 5,000. And when we do that, we get 6,416.79. So that's how much we actually have to pay back. So if we want to know how much interest we are going to be charged, we take how much we pay back minus how much we borrowed. 6416.79 minus the 5,000. So So $1,416.79. That's how much the bank is charging us to use their money. If we want to find out how much our payment's going to be, we take how much we have to pay back, and we divide that by the number of payments. So 64,1679 divided by 60 payments, so $106.95. So that's how much each of our payments would be given this scenario for our loan. So what's important is converting our rate to a decimal, plugging the values in the proper places, and then do an order of operation. Inside the parentheses first. On the inside, we have to divide before we add, and then we do our exponent, and then we multiply.